Hello everybody, and welcome to another lecture in this series of lectures on computer architecture. Let's continue with our intervals summary of digital systems, because it's always good to know where we stand. And if you already know this, you can just skip it, but never mind, it costs nothing to explain to you again. I told you in the last lecture that we have three aspects of informatics, of information processing, and that is we had the electronics part, is how the things are implemented. Then we have the logics part, which is actually the basis of all the reasoning and all the informatics. And we have then the numbers part, and that is the thing that we want to actually implement in our computer. We want a machine that is implementing, that is doing the mathematical calculations that we are doing in our head. We want to do them in their head because they're faster at this. Well, so they say. So today, in this one, I'm going to talk to you about the number systems. And the first thing to observe is that people are saying that, well, we have a nice decimal number system, actually coming from India, brought to us by the Arabians. Very nice, it's a very nice contribution to the world. And in fact, the calculations are done very simple in decimal systems, but it's not as if this is the only way that you can do the number calculations. It's just that it is more or less a convenient way to do it, and the winning thing, the winning strategy. Sometimes I hear people saying like, well, because 10 is a round number. Well, but any number in its own base is written as 10. So for instance, 2 in the binary system is written as 10, and 6 in the hexal system is written as 10. So any number would be round. Right? And the other thing I hear is that, because we have 10 numbers, and therefore 10 numbers, it would be good to use 10 as a decimal system. Well, not really, because take a look at this. If we, because we have 5 fingers on the hand, the best system to use would be 5 plus 1, that's 6. And I've given you here an example. Imagine that I use my hand, my left hand for the units and my right hand for the multiples of the base. Then something like what I've shown you here on this picture here on the left. This would be 3 plus 4 times the base. 4 times the base, it's 24. Plus 3, that would be 27. So if we have, because we have 5 fingers on each hand, the hexal system would then be the best. And the decimal system is not good for much. Moreover, it will be later clear, I want to show you that actually what we have been learning in school, which are the tables, the multiplication tables, from I learned them from 1 until 10, but it would be better to learn them from 0 until 9, meaning all the possible digits multiplied with all possible digits. So this is the multiplication table actually that a computer could memorize without thinking. It should just know it, the same as we know it. We've just been hammering it into our heads and we will never forget it. But we get all the calculations, even multiplications, are based on basically these, which is here above my head now. It's basically the memory of these multiplication tables, and then we can do all our further calculations with numbers. And to go on with this, it's not that 10 is the only way to do it. For instance, here we have the Mayas that used the base 20, and they are the ones that already had 0. Base 20, it's nice because you can do more fractions more easily. There's because 20 is divided by 2, 4, 5, and 10, and therefore it is more fractions will work out well. The Babylonians, they had even base 60, and then it's very good for when you're doing fractions because it's nearly divisible by anything, by everything. The Romans, well, let's forget them. I don't know how they ever built structures, large structures based on this number system, because it seems to me to be unworkable. What we basically did is we used a convention, which is a weighted series of digits. The one on the right gets the least weight, it's just multiplied by 1, and then successively every one to the left is multiplied by by the base. So I'll give you an example. We can use this in any base system, so we have this kind of representation, which the Romans did not have. The binary is very useful because computers are implemented in logic, in binary, in this binary electronics as we have seen. Doesn't mean that it is the easiest way to do it, but computers can do it, and therefore for computers is the easiest. Of course, now we have the problem how to implement our decimal calculations into binary. But this is what we will learn in the future also here. Actually, we didn't learn at all in digital systems how to do calculations at all. We only did logic operations. We didn't do any multiplications or additions or anything. This will be the subject of computer architecture. And then, of course, we have this funny joke, which you can see here. There are, well, I should not pronounce it. I should say something later. There are 10 types of people, those that know binary and those that don't. I hope you now get this joke, because you should be knowledgeable in binary. Now, moreover, we went on and on and on. We talked about that it's actually just a number representation. A bit pattern can actually mean anything. It's just a convention. If we say 111, that can mean 7, but it can also mean something else. It can be a character or something like this. It's just everything is conventional. The only thing that exists is voltages. The rest is convention. Then, of course, we also had the other funny systems like octal, hexadecimal, and binary coded decimal. The octal and hexadecimal, we learned how to do some small calculations with that. Nothing special. The table of this is here: decimal, hexadecimal, octal, and also if you want to, and binary. If you want to know, 0b means binary, 0d is decimal, 0x, that's very famous, is hexadecimal, and 0o is octal. Binary coded decimal is funny because it's not going efficient with all the bits. Because of all the 16 possibilities, it is using only 10. Well, we'll not delve into that anymore, at least not for the moment. Then we had how to do number conversion. And for the number conversion, it came in very handy to use the tables of either the source base of or of the destination base. And we did some examples how to convert from one system to another. And we more or less managed to do that back and forth from binary to decimal, which are the most famous, from decimal to binary. Hexadecimal, that was easy. Hexadecimal to binary, you just group 4 bits. From octal to binary, you just group 3 bits, vice versa. That was all very easy and very funny. Now, negative numbers, it starts getting a little bit more complicated because we have to use a convention how to store the negative sign. And we had 3 conventions. One was sign magnitude. You just use the first bit to indicate the sign, and then the other bits are the magnitude. The funny thing is, of course, then you have 2 times 0, you have plus 0 and you have minus 0, which is a little bit strange, if not inefficient use of all the bit patterns. And one's complement, you have the same problem. In a one's complement, negative numbers, you just invert all bits. And in two's complement, as you know, you take the complement of 2. One's complement and two's complement. These are the things that we learned. These were the negative numbers. And we didn't do any calculations yet. We just did sort of like the conversions and things like this, and to know how they represented. The calculations we start doing in these computer architecture lectures. And then we have here the Ascii, which is not a number but just a representation of a character. It's called American Standard Code for Information Interchange. Okay, what's in the name? It represents letters plus control keys. You have, in principle, 128 characters, but in modern Ascii you also have extended Ascii codes, so you have 256. So 8-bit pattern can represent one character. The problem with that is that, well, there are more than 256 characters in the world. Look alone, for instance, at the Chinese. They have thousands of them, so you need more than 8 bits to store them, and that's why we now have more modern formats, which is no longer Ascii. Just look in your computer what character mapping you're using. Finally, we also had gray code. That is a funny way that between successive consecutive numbers there is only 1 bit changing, which comes in handy sometimes, and it's just also another convention. What we didn't deal about is a floating point, because it's a subject by itself, and we will discuss this in this lectures on computer architecture in a while. Not yet, we will delay it a little bit, but later it will be coming on floating point. It will be explained. So that is basically it about the numbers. So the third aspect will be the Boolean algebra with the Huntington postulates and so on. So see you in the next lecture.